Okay, here we go. I guess we have this lecture and one more before reading week, and then you guys have the midterm after reading week. And I guess tomorrow, something like tomorrow, I'll make a post about how the midterm is going to look. And on Thursday, we'll do a bit of review on like the second half of class. And I mean, short stories, the midterm is going to look similar to the first midterm. It's going to be all multiple choice on Scantron, same style, and it's going to cover everything up to what we finished this week. That's the summary. Okay, and let's get into it. This maximum likelihood estimation stuff. But actually, something I just remembered, I wanted to just mention a slight thing about previous things we covered. So we did this whole like evaluation, business, and regularization that was covered. And on your assignments, you had to implement this regularization stuff. And then I realized that I forgot how to write code in Python, so I may have thrown some of you off, which is not a surprise considering I haven't written code in a while. But anyway, there was this part here, which was you had to calculate the gradient. And we did this calculation for the regularized empirical risk, and we saw that, oh, well, the gradient basically has this like extra kind of term that it didn't have before due to the regularizer. So let's just remember there is this like regularized term. You take its derivatives, partial derivatives, but it only starts from j equal to 1. And so the derivatives only happen for, well, indices 1 to d. And then in the pseudocode, there was this extra term you have to add to the derivative. And I used this indexing to mean indices 1 to d, including d. But as some of you may have noticed in Python, this does not include d. So you should interpret this as, you know, it includes d. This is pseudocode, so I think that's all fine. But in Python, it so happens that d is not included at the end of this indexing, so you should have put like d plus 1, or in Python, you don't even need to put anything here, so just be 1 till the end of the list. And same thing here. Okay, so anyone that, at least one person I'm sure has noticed this thing, and it's good to just acknowledge it. Okay. Actually, maybe, yeah, fine. Okay, let's get back to where we were. This maximum likelihood stuff. And we're going to finish this maximum likelihood stuff today, and we're going to get into what is called maximum a posteriori estimation, which is kind of another way to solve really the same thing I'm going to explain right now, which is, at the end of the day, we want to like minimize this true risk, the actual risk, you know, basically the error we're going to have on new data points. And minimizing it over any possible function, we call this f base, and you can explicitly do the calculation. And if you use the squared loss, then you're in the regression setting. What you'll find is that f base very naturally kind of just for a particular x, it needs to output a single value, and the value it's going to output is just the expected value, or like basically this would be like the expected price of a house for a given whatever number of rooms or something like that. That turns out to be kind of the best you can do, the optimal predictor. And if you just expand this expectation, it has, I mean, the following form, which is just the definition of an expectation. And since it's the regression setting, it's the integral of the values of your labels multiplied by the corresponding probability density of those labels conditioned on x. And one alternative to doing this whole machine learning thing is like, well, instead of, you know, minimizing this objective above by estimating this quantity, which would be something like, you know, well, okay, yeah, instead of estimating this directly, what you can do is, well, you can find out what f base is, which we have done, and just calculate the integral explicitly by plugging in an estimate of this density in here. Okay, and that's what we were trying to do, and it turns out there's like a deep, I guess, research field, or I mean, I guess topic called like this density estimation stuff, and one of the ways to do this is this maximum likelihood estimation. So hopefully it's clear that what we boiled down the problem to is just estimating a density. And in classification is going to be estimating a PMF. And so all that's left to do is how we're going to estimate the density, and maximum likelihood is one way to do it. This maximum a posteriori, which we will cover in like 50 minutes, is another way to do it. So we're just discussing ways to do this, and we'll see what kind of function we get. Okay, and then we reviewed how you do this. And the way to do this using this maximum likelihood is as follows, which is like if you had some data, and that data was, I don't know, for some reason IID, which it is in our case. So you have this data set that's IID points, which means that each one of the data points, I can think of this as a flip of a coin. Each one of these random variables is the same coin. That's the same distribution. That's the identically distributed part. And it's independent because you're flipping the coin independent of what happened before. Okay, so you have these independent random variables. And the beautiful thing is then if you look at the probability density of a particular data set, well, because of this independence, you can break up that PDF or PMF into a product. This was one of the rules we had of independence. It's very nice. And then the identically distributed thing allows us to substitute each one of these PMF or PDFs with the same thing because they're all the same distribution. And you just end up that for n data points, the probability of getting a particular data set is just the product of getting every single one of those things. So that's like if you flip a coin 5 times, and let's say the probability of heads was like 70%, well, the probability you get 5 heads in a row is just 70% or 0.7 multiplied 5 times. Okay, so that should make complete sense. And so you see this data, right? But you have no idea what the distribution was that generated the data. And that's really the thing we're trying to find. And so the question is like, what should you pick? Like if you had to pick some PMF or PDF generating the data, what should you pick? Well, we can calculate this for various PMF or PDF. So we can try different P's in here, get different numbers. And then we can be like, well, I mean, maybe a reasonable choice is the one that makes, you know, the probability of the data the highest value. And this idea of like searching over P's for a fixed data set, because you've gathered the data already, is this idea of, well, first of all, people give this thing the name of the likelihood. And so you should think of the likelihood as a function over P's now. It's a function over different PMFs or PDFs for a fixed data set. And so these different PMFs or PDFs will tell you that the probability of that particular data set is some value. And you're trying to, well, then the question is like, which one should you choose? And the logical choice would be maybe the one that makes this likelihood the largest. And once again, likelihood should be thought of as a function of P for a fixed data set. And so, in other words, you're kind of just trying to pick the most likely P given your data. So hopefully that makes intuitive sense. And then what we did is I mean, at this point, you're basically kind of done. It's just a mathematical exercise to solve this optimization problem, which is all that we're really doing next. And we already know how to solve optimization problems, right? Like, I mean, usually we had argmins here, but you just take the derivatives, set it to 0, or do gradient descent. And that's really all we're working out next. So we did the case for like this coin flip stuff. I'm not going to go over it, but you know, we had this, like maybe I just say the picture, which was like, if you flip a coin 5 times and you end up with like 3 tails, that's the 0, and 2 heads, well, okay, like intuitively, you're probably going to guess that the original distribution generating the data was probably more likely to, you know, give you tails than heads. And it turns out that the actual value for this like maximum likelihood, if you solve it, which we don't do here, but we, I think, end up doing for classification later, is just going to be the ratio of heads over all the coin flips. That's the probability of heads. Or in other words, the probability of tails is just 1 minus that. So if the probability of heads is 2 over 5, then the probability of tails here would have been 3 over 5, which is also kind of what you would intuitively expect. Okay, and now we get into the example we were working with last time. And this is, If you understand this, it's really helpful because it's going to be essentially the same set of kind of assumptions and steps that we're going to use for this regression setting. And in the regression setting, our labels are continuous. They can be like any real number, let's say. And in the example here, we're still not doing machine learning. We're still doing just, you have some random variables. Here it's going to be the height of a person, but this will be very related soon. Okay, so what does this example say? It says we have these random variables that they represent the height of the ith person that you've gathered their height information. And for some reason, and this seems to actually hold true when you gather people's height for some reason, which is that it follows a normal distribution. And so people's average height has some average, that's the mean of the normal distribution. And the variance is probably not 1, but it turns out that this makes the math easier. So we make the simplifying assumption that the variance of people's height is 1. Okay, fine. And all that really says is that the PDF looks like this. It just has this is the normal distributions function for the PDF. And this is the true PDF, or the true PDF of the true distribution generating the data, indicated by the fact that the parameter mu star has a star. That's the true mean of people's height. And of course, we don't know this. The whole goal is to estimate this from some data. And we need to solve this MLE problem, which was this whole argmax business. And in that argmax, we needed to choose, we needed to pick this P. And the natural choice for the P is, given the assumption that things are following a normal distribution with some unknown mean parameter, is to assume that we're taking this argmax over a class of distributions such that a class of PDFs, such that each PDF is of the form of a normal distribution. And here I made a mistake, which this mu star, of course, in here is just mu. So each function in here has the following form for any mu in R. And mu star, of course, belongs to here, but it's only one of infinitely many choices for mu. And so then this whole maximum likelihood estimation equation ends up, you go back up, it just ended up being replace P with that PDF. And since there's a one-to-one correspondence with each PDF and the parameter describing it, which is the mean, mu, taking the argmax over PDFs is the same as taking the argmax over the parameter, plugging it into the PDF and using that PDF. And so that's what the process looks like. We've seen this before. And this is often how a lot of optimization is done. You can't optimize over functions, but you can what is called parameterize the function class. So describe your function class as a set of functions that are described by some finite number of parameters, like mu here only. And then you optimize over just that. So anyways, the maximum likelihood estimate for the mean parameter, which will fully describe the normal density, right, is the following. It is, you take the argmax mu over the likelihood function, which is just the product of the corresponding PDFs, all parameterized by mu. And this is, notice how this is like a function of that fixed data set we have. So there's n data points here, and we take the product of each one of the corresponding PDFs with that data point plugged in to the PDF. Okay, and then the way we map this to optimization world is we say, oh, this is just a function. It's like g of z that we've seen before. Here, of course, I made a mistake because g of z is not a function of z, it's a function of mu. Parameter is now mu. Yeah. And so you just want to take the argmax of some function of mu that has some form. We're going to need that it's convex, obviously. Well, for maximizing, you need the opposite, it's concave, but we'll talk about that. And we're just going to try to use our tools from before to basically do that. And that's what we were trying to work out last time. But before doing that, I just maybe remind you once again of this example, which is if you were to gather a bunch of data points, like 9 data points right here, all we're really saying is we want to pick the density, which is like this bell curve. That kind of makes the data, well, for the fixed data, which like we're trying to pick the density that you think is like the most likely density to have generated that data. And a natural choice is kind of something like this, I guess. And what we're going to find is really since each density is described by its corresponding mean or expected value, we'll find that this is going to be exactly the density that has the mean mu parameter equal to the sample mean over our data points, which should intuitively also make sense. So I already ruined this last time saying this is going to be the solution we get to, and now we spend like a page and a half doing some math to get to that. Okay. Any questions before we just really solve this optimization problem? Okay. So yeah, we just want to solve that optimization problem. We start with this is kind of the canonical procedure you should remember when working through these maximum likelihood problems. It kind of always follows this structure, which is you want to solve for this. This is equal by what we had discussed earlier as the parameter mu that maximizes the likelihood. And the likelihood is this product of these PDFs or PMFs. Here it's a bunch of products of PDFs. Each PDF is a function of mu. We originally were writing it like this. It's parameterized by mu. But people like to kind of abuse notation and write that it's conditioned on mu. So like for a given mu, you get a different p. It's much more clear here. This kind of is deceiving. It makes it seem as mu is some random variable you're conditioning on, which is not the case. But we will continue with the convention and start using this from now on. Okay, and so we want to maximize this. And the procedure you do is, well, first you change the maximization to a minimization problem, so you take the negative of this. And that's all fine, we'll do that in a moment. And I'm doing it in the order that seems to be presented in all sorts of other places. So you could just first apply the negative and get to a min here, argmin, and you minimize the negative of the function, that's all fine. I'm just gonna do this in this order because you'll see it in every other course in this order. Okay, and so the observation is like, well, the way you do this is probably take like the derivative of this thing and try to set it to 0 or do gradient descent. But since this is a product, it's very ugly to take the derivative of like the product of n things. You need to apply this product rule. And there's this wonderful observation that it would be really nice if we didn't have this product. The log function, if you apply it to a product, is the same as the log of a bunch of products. So like the log of a times b is the same as log of a plus log of b. So really you get this property, which is the log of a bunch of products is the same as the sum of the logs of the things. That's really nice because now you just get a sum of a bunch of things. We know how to take derivatives of sums. There's no product rules or anything. Why is this okay? Okay. Why is it okay to apply this log? And it's okay because I said this thing, which is like it's monotone increasing. So log is a monotone increasing function. And if you apply that to a function that has some, let's say, global maximum in this case, then it won't ruin anything. So the maximum or the argument that achieves the maximum will stay the same. And then I drew a really poor photo here, which was in various ways incorrect. So that will go away now. And today I had some fun plotting some things, which will maybe make this a little more helpful on Desmos. And just in general, I would recommend plotting things on Desmos a lot in life, because usually the math is kind of maybe less descriptive than drawing plots. So this is a common thing that a lot of, at least people I find in research like to do, is they like get some equations, they don't know what they look like, they go plot things, and then they get a lot of intuition. Okay, so let's just plot what this might look like for one data point, because that'll make things easier. So if this product, if you just have one data point, is just one of these, just Z1. And that's just the PDF of a Gaussian. So that's like this. Right, we've seen this equation before. And that's for a single data point. So Zi equals to 1. That's what that looks like. Oh, getting a phone call from Wisconsin. That's interesting. Okay. Okay, so that's our function, right? This is the function, which I've used x here in place of mu, because Desmos uses x. And we try to maximize this function. We try to find its argmax. And visually, that's easy. It's just here. And our single data point is this purple point here. Okay. And okay. And so that's the likelihood function for a single data point. But it turns out that like, okay, well, if we add the product of them, it's going to look like a bit different. But anyways, so why is the log not going to ruin things? Well, the log's not going to ruin things because this green function is the log. And notice that the log is just, it never changes from increasing. It's always like getting bigger. If you take some point x, it's at another point x later on, it's always gone higher. Okay, that's what it means, monotone increasing. It's, in other words, it's non-decreasing. It never decreases. Okay, and the reason that's good is because now what's going to happen is we're going to take this black line, and for every single y value, we're going to plug that in through the green function. And we get the red function below. And how does this make sense? Well, it's going to make sense because what's going to happen is you take any point of this black function, and its output value is now getting plugged into the green function as the x value of the green function. And notice that as the value of this black, like as you get larger and larger x values for the green function, you get larger and larger outputs, right? This is where the increasing part is important. And so at this point, when you plug this point of the black function into the green function, you're going to get the largest value. And any other y point, you will have a smaller value from the log of the green function. So this point here will still correspond to this point here. And we can even see how we got this value here, right? It's like, well, at this point, it takes on the value of something like 0.4 maybe. And what is the green function, the log, at 0.4? Well, this is 1, so 0.4 is somewhere here. So the green function at 0.4 is like somewhere here. And so that's going to be our new function, which is the log of the black function. So you get, at 0.4, you get a value of something like this. And everywhere else, this black function takes a smaller value, which means you're going to get a value smaller than the value at 0.4. So you're going to take on some value that's like one of these points. And that's where all these points on the red line are. Okay. This is a very in-detailed explanation of how applying this monotone increasing function will not mess things up for an argmax. So the argmax stays the same. And then we did this step, which we're going to see, which is like, if you want to do, we've always done minimization. So we want to change to a minimization problem. So if we have for maximizing a function like this, then if you take its negative, which is the blue, then you can minimize this function and the argmin and the argmax match. So that would be the value on this x-axis match. Of course, the actual values they take are different, but that doesn't matter for us because we just care about the parameter that achieves this. So that's why these steps are all okay. And you can also see from this that we get a nice well, this is a concave function, but once we take the negative, when we're minimizing, we have a convex function. And roughly speaking, you can just see that when you take the log, the exponential goes away, and you're just left with a quadratic, and in particular, a negative quadratic. So you're just left with a parabola, which we know is concave. The negative is concave, and the positive is convex. Okay, so that's what all these steps did. Hopefully that clarifies some of this stuff, because all of this maximum likelihood estimation follows these steps, which is you take the log, and what you get here is the log likelihood. And this was also some poor labeling, because really it's I'll label it here, it's this whole quantity with the sum is called the log likelihood. And then when you take its negative, so that you're minimizing, you have the negative log likelihood. So makes complete sense, I think. Okay, and now with all these like minor details, now we just actually solve things. So that just means we actually plug in what the density is and just work out some math now. Okay, and this procedure, you're going to do it a lot. Okay, and so let's do that. So we have everything still here is the same, except now we just need to plug in the definition of the density into the log. So let's do that. So we're going to have log, whoops. And what's the density? Well, this is why I kept this around. So this whole argmax product thing, forget about that. But what I need is this quantity. That's the density. I put it into there. Parameter of mu. So this whole thing is a function of mu. And we're going to try to minimize it. Okay. And so maybe it looks a little bit complicated. But things will get very simple very quickly. So first observation is you really should remember this property because it's going to help you a lot with logs. Oh, and another thing, as I've mentioned earlier in this course, log always means the natural logarithm because I will never remember to write ln anywhere. And somehow anywhere other than, well, in machine learning, log always means natural logarithm somehow, but and in math most of the time. But when we work in computer science, we use base 2 or base, anyways. It's just natural logarithm from now on. Okay, so yeah, there's this property, right, that when you multiply two things, you can get a sum. So notice here, this is a constant times something. So we're going to make use of that property. And we're going to get the following. Okay, maybe let's make some more room. So you're going to get that the log of the product is equal to the sum of logs. So first, it's a log of this plus the log of this. And that's all in the sum. So that's all in the sum. And now there's an observation that if I have a function and I shift the function by a constant up or down, it clearly does not change the argument that maximizes or minimizes it. We can even see that visually. Like if I took this blue function, and now what I'm doing is I'm literally adding to it. Well, okay. It's breaking up in it. But like if I took this blue function and added some amount vertically, it's not going to change the minimizer. So this doesn't change the argument. So we can remove that. So this is an equality again. So just remove that. Great. And yeah, we stepped through this in painful detail the first time around. And later on, we will not do all these steps so slowly. But for now, we do this one by one. And now we make this observation, which is really where we were trying to like, well, okay, one of the nice things about using this normal distribution is now you end up with the log of an exponential. And if you remember, the log is just saying e to what power gives me the thing inside. Well, clearly, it's e to the power of the thing inside. So the log and the exponential cancel. Okay, let's just go downstairs. Oh. So log, exponential, they cancel. And we get this. That simplified things a lot. And let's just do it in this step too. You get the negative times the negative makes this a positive. And now we get our squared function, which we just saw below already. But we just get a sum of the squared functions. But that's all fine. Great. And now, this is a super easy function to optimize, right? Now look at now we're just taking the argmin of like this thing, which is now we'll call like our g of u in optimization world, g of mu. And that's very easy to optimize. We can just take its derivative and set it to 0. It has a closed form solution. So let's just do that. So the partial derivative, and maybe I'll do this in blue as like a intermediary thing. Partial derivative in terms of mu of this thing, right? Well, what is it? It's just the derivative of this. This 2 comes out. Yeah, it's a sum of a bunch of things, but you can take the partial derivatives of each of the terms in the sum. So I'm just skipping all that. And 2 comes out here. Take the derivative of this, you get a negative. And yeah, we get the following thing, which is negative. The 2 came out. I'm going to pull this 2 outside as well. Negative 2 over 2 of the sum I equal 1. And the negative, right, is this came out here. Sum I equal 1 to n of the same quantity, zi minus mu. And we want to set that to 0. These things cancel. And so what we end up with is taking the negative zi sum to the right-hand side and minus mu with minus, and it's summed up n times, so that's just n times mu. You get n mu equals to sum I equal 1 to n of zi. Right? Which tells us that the maximum likelihood parameter, which is the solution to this thing, for mu, is just equal to 1 over n sum I equal 1 to n of zi, which is just the sample mean we had originally said it was going to be. Okay. So that's how the math gives you that. Now, let's make use of this new tool to solve the machine learning problem we were interested in at the beginning of the class. So I'll just do that on a whole new page down here. And let us recall what we were trying to do. Okay, so just for this, we want to estimate this quantity, which is the conditional density of the label y given some feature x. Yeah. And then we're going to plug it into that integral and see what our estimate of f base is. So that's our goal. We're estimating p, well, it's like little p, the density of y given x. And we're going to use maximum likelihood for now. And how does this look in our case? Well, it looks like this. We have this data set. That data set looks like this. It's these xi, x1, y1, up to xn, yn points. These are like the zi's we saw before, z1 up to zn. It's like the coin flips or the people's age. It's a multivariate random variable. That's okay. Okay, we've seen this a bunch of times. This thing has like some joint distribution over, well, it has some distribution over the whole data set. That has a corresponding PMF or PDF or mixture, complicated looking thing. But the lovely thing is, similar to the case above, these xi, yi's are like the zi's, and they are indeed, all right, IID. This is written sometimes like this, IID from the same distribution P of what we called X, Y. And there's a corresponding PMF or PDF, which was this little P of X, Y. Okay, and here, at this point of the whole estimation business, we wanted this thing. So let's do first one observation, which is using the chain rule, right? This quantity, this quantity, which is the PMF, this PMF or PDF, can be written as the conditional of the label given a corresponding feature, which is written as like y given x, times the marginal of x. That's the chain rule of probabilities. And so that's going to help us estimate this, because we're going to essentially try to do this MLE procedure to kind of estimate this quantity. And we're going to see that in there we can decompose it as follows. And we're only going to make an assumption on the following term, which is this. Sometimes it's made on this as well. We're not going to make any, we're just going to say we don't know what that is. It has nothing to do with any parameters that we were going to try to estimate. We're just going to make an assumption on this distribution, or this PDF, because it's a conditional PDF. And we'll see what happens. Okay, and what is the assumption we're going to make? Well, the assumption is going to be something like this, and maybe I draw it first, and then we'll describe it. Oh, and maybe the best way to do this is, let's take the plot we had earlier. So this was like maybe f base, and then there was all this like data that we were using to kind of understand what that distribution that's generating our data is like. And maybe I'll move this down. And the question we're trying to ask is like, how should we model this the data generating distribution? Okay. And we're only going to model the distribution of y, because that's all we're going to need to calculate f base, right? That's all we need to estimate is the distribution of y given x. And what should we assume it is? So the way you should think about this is that the probability of y given x, that's like if you fix an x, what is the distribution of the points y along this axis? And if I fix x here, what's the distribution of y along this axis? Well, it probably depends on x, first of all. But then, like, how is it distributed? And, okay, like the answer is we're going to assume that it's normally distributed. So for a particular x, you can think of it as it looks like this. It looks like there is that's the distribution of y given x for a particular x. And at a different x, it's like this. So the mean is going to change with a different x, but it's still going to remain normal, and we're going to assume it has variance of 1. Okay. And so formally, the assumption is as follows, which is p of y given x for a particular value of x, which okay, let's just write it like this. Okay, So this is a function of y given x. And what does it look like? Well, it's going to look like this normal distribution, which we've seen before. So let's just take the PDF that we've seen before, like this. Or even better, just take this. And there's some things we're going to have to slightly change. Okay, so the first thing is that the point, right, we fixed x, the points are just the values of y. So the z is changing to y now. And for every single x, we said, oh, it's going to change. Like, what's going to change is the mean. The mean of the data generating distribution is going to change, and it's going to depend on x. And so it's not going to be mu star anymore, but it's somehow going to have to be a function of x. Okay, let me make some room here. So this mu star, I'm going to have to erase it, and I'm going to have to like make it some function of x. Let's call it h of x. It's going to be like h star. It's going to be like the true function of x that determines the mean. Oh, and maybe here's a step that makes things even simpler. This was the PDF of this, whatever. But in other words, before writing this PDF, I could have just said that p of y given x, this whole distribution of y given x, is going to be normally distributed, right? Oh, sorry. The random variable y given some x, some value of x. Well, that's going to be, the assumption is that it's going to be normally distributed with some mean, and that mean has to depend on x, as we've seen, or it naturally depends on it. And the variance is 1. Okay, so that's going to be the assumption we have, that there is some that this is the distribution of y for a particular x. It's normally distributed with some mean that depends on the value of x, which makes sense. If it was maybe like a linear trend, it would just mean that this mean value is that. Okay, and as you can see, if we want to optimize over this parameter, we're going to need to take this maximum, like we're going to take argmax, and argmax is over the parameter of the normal distribution. Now we have this really ugly looking parameter because it's itself a function, and we don't really know what to do with that. Okay, and so the next kind of simplifying assumption that is made is to make a choice for this function of the mean. So what's like a function that we should pick for this mean? And the function we're going to pick is, well, it's going to say like what, like this is, so this plot here is kind of like this f base is the mean of each one of these points. And so, well, if we wanted to represent something like this, we need a complicated like polynomial. Well, we're going to start simple, and we're going to say that, oh, well, we assume that, you know, the data is on a line, okay, so that the mean follows this linear trend. So if you increase x, the mean is going to change like this for now. The obvious extension is going to change things to polynomials, but for now, that's going to be the assumption. And so the way we're going to model that is we're going to replace this h star with a linear function. And the beauty is that if you change it with a linear function has a parameter that describes it, right? And so in other words, the function of x we're going to use is x transpose w star. Okay. And so this is like, yeah, this is our assumption. Our assumption is that f, like basically the thing that's generating the data, right, the labels, first of all, its mean, which would be like, it's going to be the same as f base, is actually, okay, let me say this in another word. This value here, like just an observation, is that this value, right, which is the mean of the normal distribution, is the same, like the mean, what does the mean mean? It means the expected value of the random variable. So this is the expected value of the random variable of y given x, right? Which is exactly f base. Okay, so the first assumption here is that, well, the mean, or f base, follows a linear trend. And not only that, but also that the data has this normal distribution around that x for all the y values. Okay. And under these assumptions, now we're going to work things out and see what we get. Okay. Yeah. Sorry? Because I forgot to do that. That's going to be squared. And we're coming, yeah. And I need to replace h star with the corresponding linear function. So it's going to be some, yeah. I cut myself off short before when we came back to the above. So yeah, this happens, and maybe I should, oh. So this is the assumption. So we're going to assume this. Of course, this is not always the case. But yes, if your data was following this linear trend, and maybe the y values, if you have enough of them for a particular feature, really do follow this normal distribution, well, then this is sort of reasonable. Okay, and then what this says is that, well, the PDF, this is just looking up the PDF of the normal distribution, is this y minus the mean. We know the mean is now x transpose w star squared. And then it's 2 times sigma squared usually, but sigma squared is 1, which is that variance that we have chosen to be 1 here. And you can all do this in more generality, and you can get the equations for sigma and make choices for that. But for the purpose of this, we're going to make this simplifying assumption, and we'll see what we just get because it's interesting. Okay. So that's a long discussion on the assumptions we're making here for this setting. But once we've done all that, we're just back to the usual procedure, which is calculating the maximum likelihood estimate of this parameter. Okay, and so we want to get an estimate of this thing, this w star somehow. And that's going to look like this. So we want to estimate w star. We're going to call this w MLE. And how are we going to get this estimate? Well, it's using the same maximum likelihood equation as before. We're going to take the maximum, the arg maximum, over all parameters w in r of d plus 1. Right? That's because, and I'm not writing out explicitly here, but the functions we're considering are going to be all of the following form, right? The same as above, like that h class that we chose above is going to have all functions that are of this form, because we know that the true parameter, or sorry, the true function is the following. It actually has a w star, and that w star is in rd plus 1. And so one of these w's is w star, and we would like to estimate it. And now here we plug in the likelihood, which is this product from I equal 1 to n of this p, which is the PDF of, all right, like this, of xi, yi, conditioned on, and this is really you should say it's like parameterized by, sometimes people do write a semicolon here, but we'll keep this, and parameterized by this parameter w. So each one of these, if you change w, you get a totally different PDF, right? Described by this. And yeah, and so we want to maximize this likelihood equation. Okay. Notice, well, yeah. So let's just do the same procedure as before, and then we'll see where we apply. We can apply the chain rule right away, actually, but we'll just do it a little bit later. Okay. So we do the same procedure, which is the first step is to take the log and then simplify the product with the log. So what that means is you remove this product, you apply the log, the max stays the same, and now you have the log, oh, the log's inside, you have the sum I equal 1 to n of the logs of this. Then you take the negative to get the negative log likelihood. And then the max changes to a min. Okay. And now we'll apply the chain rule that we already saw above. And I'll make some more room here. So this equation is now going to change to P of y conditioned on xi. And now this gets a little bit sloppy, but people put a comma, and now this is parameterized by w, okay? Which really is like, this is an actual parameter. This is the thing you're actually conditioning on that's a random variable, but people still write it like this. And that's just like the usual chain rule. So here's how this is going to work. The chain rule is like this. There's no w's. But now, because we say, oh, each one of these functions can depend on a parameter w, we add this extra, like, you would write a conditioning of w here, and it can add the comma here, and we're going to add the w here. And that's how that works. So I'm going to continue with the chain rule here. So you have xi. These are vectors parameterized by w. Okay. And now the observation is, well, two things. So the log of a product is going to be the sum of the logs. And this quantity here, we made no assumptions on, it has nothing to do with w. W doesn't change what this quantity is. We did not assume anything about it. So this is just going to be a constant. And so I'll break this up into two steps again. But yeah, the log of the product becomes the sum of logs. So we have a big outside thing. We have this. And you end up with the log of the product is the sum of the logs. And the observation here is that, once again, if you're minimizing over a parameter or a function of some parameter, and you add a constant, so the other observation is that this p, this marginal of xi, has nothing to do with w. We didn't make any assumptions about it, so it's just some TDF of x, and yeah, it has nothing to do with w. And so it's just a constant with respect to w. And so it does not change the minimum here. So we can just completely remove it, and we can just minimize this term. And there's various versions where you do assume something of this. It has its own distribution, which you choose for various reasons. And we don't do that in this course, but you can do it. Okay. So we remove that because it has nothing to do with the parameter we're optimizing over. That simplifies things. Okay. And now we just plug in the corresponding equation for this, which is the PDF of a normal distribution that we saw above with parameter w. So let's do that. And now you're going to see that this is going to look very similar to what we've done before in the case of people's height. So I'm just going to go up here, take this expression, and now I'm going to replace w star with our parameter w that we're trying to find. We're trying to find the w here that's going to make this quantity the largest, this likelihood. So w star is no longer w star, it's just w, the parameter we're searching over. And I guess we don't need this. And yeah, that's our expression. And now I'll take the luxury of you remembering that the log of these two things, which is a product of two things, is the sum of the logs. And the log of this quantity is just going to be a constant as before. And it's not going to change the value, the argmin. And so this 1 over square root 2 pi can just be forgotten. And so we're just going to end up with the log of this exponential. So let's just do that step. And notice the equality. Everything's equal. So this goes away. So we end up with this expression. And now we apply the same procedure that we saw before, the log of the exponential. Well, that's the same thing as they cancel out. So this goes away, this goes away. And isn't that all wonderful? because now we end up with a really simple expression. The minuses also cancel. And look at that. We're now minimizing a squared function. And let me rewrite this in a slightly different way. Okay. Some things to note. Notice that, well, first, okay, let's just do a bunch of things. First of all, that if you have a function, like in this plot above, if you multiply it by a constant, which would mean just like stretching it out, the minimizer still doesn't change. So same with shifting it up and down, scaling the function. Is not, oh, sorry. Yeah, scaling the function is just going to change it like this. Or maybe it'll go like this. But the minimizer is not going to change. Like if you multiply by 2, this minimizer is going to go up 2. All these points, or sorry, it's going to go down 2, I guess, because it's negative. All these points are going to get scaled down, but it's not going to change the corresponding function's minimizer. So this 2 is not going to change the minimum, is the point of the story. Okay, that's one observation. Second observation is that if you square something, that's going to always be positive. So it doesn't matter if I do y minus this or this minus y. And the reason I'm going to change these around is because the version we've seen when we were minimizing the empirical risk is the following. We always said, oh, let me just clean up something. So up to now, we had these data points xi, yi. And at this point, when we plugged in the PDF, we need to make sure these are xi, yi as well. So these are all xi, yi, xi, yi. And now this becomes a little more clear. Notice that this almost looks like the squared loss of our predictor in what we were doing before, right, in empirical risk minimization, minus the labels. I'm just going to move them around so it looks exactly the same as before. So this will be yi, this will be xi. And we always wrote the predictor minus the labels. These are equivalent still. And then finally, we had the sample mean. So we had 1 over n out here. And that's still completely fine to add because once again, that's just a number scaling the function. So the minimizer, the argmin, does not change if you scale by another constant, independent of the parameter w. Okay. That's really nice because if you remember, this quantity is just the empirical risk. This is L hat of W that we've seen before, where this is the linear predictor we were using. Okay, so that's curious. So that turns out that, I mean, well, what it tells us, told us that, this is what we wrote at the very beginning, that the MLE solution is the same as the empirical risk minimizer parameter. Okay. But we still haven't gone to, okay, so that's what we got. That's what the MLE thing is. We know how to solve this. Okay. We also know how to solve this equation, right? Like this is going to equal to that expression we've seen before, which is that like A matrix inverse times the B vector. Same thing for that closed form solution. Or you could do gradient descent, or whatever you want. Okay, but what is that all gonna like? Okay, so we got this mu MLE, which tells us that, okay, well, if we made these assumptions, then our best choice of means for each one of these labels, our best choice will be, our best estimate of W star is going to be this mu MLE. So we got this distribution in some sense. So we have this distribution of y given x. But we don't have a predictor yet, right? Well, like we need to like, all we got is the mean of this distribution. How are we going to predict? Well, remember to predict, we need to, the way we're going to do this is we're going to estimate f bays by using this PDF and plugging it into that integral and solving. So in other words, let's go back to the original objective and see how this all pans out. So we had this. And now we finally have an estimate of the thing inside the integral. We have an estimate of the PDF of y given x. So let's work out the details. So now this step is going to be our approximation step. We're going to be like, oh, well, this is approximately equal to And maybe one other way to write this is this thing above, we made the assumption that this was the PDF for W star, based on W star. That's the true PDF. We made an assumption of what it was. And now we're replacing it with our estimate of W star, W MLE. That's just an estimate of this integral because we've replaced the above with the below. And what does that give us? Well, we can say that, I mean, if this is a different PDF, then we can say that, oh, this looks like the expected value of some random variable y given x with the following PDF, right? So we could say that, oh, well, this kind of looks like, I mean, it's exactly equal to the expected value of some new random variable y prime given x is equal to little x, just like above here. But now the y is different. The y prime is going to be, so where y prime given x equal to this little x is going to be distributed based on a normal distribution that has mean x transpose W MLE now, and variance 1. While above, maybe I should have, well, we know what above is. This y given x was distributed like this, but not with W MLE, but with W star, right? Okay, that's really wonderful because f base is now, our estimate of f base is this. So all we have to do is calculate this integral. Guess what? It's really easy to do that because the expected value of this is just exactly this parameter, or like this quantity here in the normal distribution. So you could calculate this whole thing and you will find, if you plug in the corresponding PDF, you'll find it's just this. It's just equal to exactly the mean parameter. Okay. So at the end, you end up that x base, our estimate of it is going to be x transpose W MLE. Okay. And above, we saw that WMLE was the same as the empirical risk minimizer, W parameter. And so this is, well, it's the same as that kind of like f hat function we've seen before, which is that f hat of x thing, which was, yeah, where f hat is equal to the arg min f in our function class that we chose, which was those like linear functions before, of L of f, L hat of f. These are all the same things. This L hat of f, well, you change the functions here to, okay, we can actually write this. It's exactly from the function class f1. Okay, so there's this wonderful equivalence. It turns out that another way to think about what the empirical risk minimization solution that we've been getting when you have a linear function class is doing is it turns out that it's also exactly equivalent to assuming that for every single x, the data is being generated from a normal distribution with mean that follows a linear function of x and has a variance of 1. Okay, so at the end, it feels like we didn't really get anywhere. It's just another view, and some people go teach this first and then, or teach the ERM way. But the nice thing is that when we get to classification, this will somehow be a more natural way to get to the corresponding predictor as opposed to doing it through the empirical risk way. And then we'll find the equivalence again, and we'll see what was the corresponding loss and stuff we should have chose. So we'll see that for classification. And yeah, and the reason kind of there is because it won't be obvious like how to, because the loss there is going to be the 0-1 loss, if you remember. And the 0-1 loss is this has a discrete jump, and it makes things not convex. And then you somehow need to like choose a different loss there, and it's not going to be kind of obvious what you should pick. And one way to, I could just tell you what the loss is, but an alternative is to go through this MLE approach, which we will do, and arrive at some sort of equation like this at the end, right? We arrived at this expression here. And then we'll see, oh, what is the corresponding quantity in here? And whatever that is, that's going to be the kind of the loss we use for classification. And that maybe brings more motivation of why we choose that loss in classification. It's going to be called this thing called the cross entropy loss. And if you were just to present it outright, it is kind of odd why you would try to do that. Okay, so that's why we kind of taught this. And now we're going to talk about a different way to kind of estimate this guy here, this conditional PDF. And what that's going to give rise to is regularization. Because right now we ended up with an objective like this. And this is just like the LHAT objective, and there's, okay, and then we saw this regularized objective, which like penalizes weights with this extra thing. And now we're going to see the kind of people say this is like the probabilistic view of regularization. Okay, so let's see how that's going to come about. And that's going to be a topic called maximum a posteriori estimation, which will be a new, I guess, set of notes for that. And before that, I answer some questions. And the question was, how do we assume the variance is 1? And the answer to that is that that's just a simplifying assumption, and you can assume it's something else. And then you'll have another parameter, and then you end up with an argmax over like a W, and another parameter describing the variance, which in general will be a matrix. It's going to be like this covariance matrix, and things get more messy. In 1D, it's easy to like work it out. Like for people's heights, you could have assumed the variance had some parameter. You end up solving. It's also going to turn out like a sample mean, so it's not that, I guess, interesting. And yeah, you get different things, and you can make, I mean, okay, this linear part as well. You can change this to polynomial features, so you could replace this x transpose with the phi function that maps it to a polynomial, and you will exactly end up with the normal version, like the thing we've seen before, with this L replaced with LP, where you end up with the polynomial features of degree P. And so that's the nice correspondence. And what that would mean is that in this plot, if you use polynomials, the mean really could follow a trend like this. Now, so far, this linear assumption meant that f Bayes, our assumption was basically that f Bayes was this, a line. But that's clearly didn't lose too much because we can do this polynomial extra mapping. Okay, well, let's get into this next topic now. This map, people call it map. And it stands for maximum a posteriori estimation. Unlike MLE, they did not add the E at the end, so it's not map E, it's just map. And now I will try to find these notes on my computer so I don't mess anything up. Okay. So it's called maximum posteriori estimation. And then people just call this map. Okay, and yeah, so you remember we want to estimate this conditional, same motivation. We want to estimate, okay, want to estimate this thing, the conditional PDF of y given x, because if we had this, we could then plug it in to get f base. And we did MLE to do that one way using the data set we had. And that looked like this. So let me just remind you, MLE said something like this. It said, oh, okay, well, let's pick the argmax kind of like P. Okay, like really it was like P and some set of functions, H of, well, okay, before I make this a little more general, there was, okay. I'll write it like this. There was, before we ended up breaking things up into this product, we had that there was a PDF of the whole data, and then you had this probability of, or the density or the PMF of the data given. Okay, well, it's just this. And then you broke it up into this whole product thing, and then we said, oh, each one of those P's inside the product is parameterized by something and so on. And people will write this, and I'll write it like this just to make the kind of the idea more clear. So then we said, oh, things are parameterized by W here. Really, that means when you write out the product, each one of those functions inside is parameterized by W. And then the argmax was over these W's, which was in some set, let's call it calligraphic W for now. And in the case of machine learning, this was like RD plus 1. In the case of people's height, this was just R. It was just the parameter mu. Okay. And for every single W, you end up with like a corresponding new, a different kind of PMF or PDF inside that product. And we called this like the likelihood. Okay, and we should think of like, that's the likelihood of that parameter. So that's a number that tells you what is like, people use, it's the likelihood of a parameter. So likelihood is to be thought of as a function of parameters for a fixed data set. And it's the likelihood of these different parameters, and you want to pick the parameter that has the highest likelihood. Okay. And in map, we're going to treat things a little differently, which is now we're going to say, oh, you know what? Maybe I have some like prior knowledge on what this parameter might be. Maybe like I think the parameter is probably, I don't know, maybe for people's height, maybe it's like around 160 centimeters or something. So now I'm going to treat this parameter as like actually having a distribution. And therefore, it's going to be treated as kind of a random variable. And we're going to talk about, I want to pick the, okay, I can still write this. Well, actually, it's going to be different. It's now going to be the PMF or PDF of the parameter given the particular data set. And now I'm actually treating the parameter as a random variable. And this is going to be its corresponding conditional PDF, I guess, because it's going to be continuous. And I'm going to try to maximize this. Okay. And this might be a little bit cryptic. And so we're going to like expand this out a little bit to get an idea of what it's saying. Okay, so this is what, and maybe I should just write this. So for MLE, our parameter WMLE was just equal to this. WMAP is going to equal to this. Okay. Now, since W is a random variable and D is also your random data set, we can use different rules of probability because this is really a conditional. And one of the rules is, well, we're just going to use, okay, we'll do this in multiple steps, but like you can just use Bayes' rule directly. But I'll just break it up in 2 steps. I feel like it's nicer. So you might remember a conditional PDF has the property that it's equal to the joint divided by the marginal. Okay. And so here I'm like abusing notation. This was like this was the P, which was the conditional of W given D. This is the joint. This is the marginal. Okay. And now the top thing, using the chain rule, can be expanded in the other direction. So in other words, you can write this as the probability or the PDF of D given W times the marginal of W. And these 2 steps together are called Bayes' rule, which you change this to be the density of D given W times the marginal of W. Okay, and these together, this, okay, maybe I should write it here. This step is called Bayes' rule. This is just like the definition of conditional densities. This is the chain rule. Okay, anyways. So the point is we get an expression like this. And now it's to be interpreted this way, which is that, first of all, the denominator has nothing to do with the parameter. It's just the probability of some data, nothing, there's nothing that didn't condition on the parameter at all. So this can be removed. It doesn't affect the argmax. It's just a constant scaling the whole equation. And maybe I'll do that first. So the argmax will remain the same. And we're left with the following expression, which you might notice is just the likelihood times something new, which is actually called the prior. And this is our distribution over the parameters. It's our prior kind of knowledge of what we think the parameters might be. Another way to think about this is if this prior if it was like you were indecisive or had no reason to believe it's some value over another, you could choose this to be the uniform distribution, which says it's the same probability of being any value. And then you would just end up with the likelihood. So in other words, what we were kind of doing before can be thought of as just solving this map problem with no prior knowledge on the parameter. So we just assumed a uniform prior, and it would just be the likelihood. Okay. But now in the case where for some reason you think, well, I don't know, people's heights clearly is not negative, so at least I should think it's more likely to be some positive number than a negative number, and it's probably over like 100 centimeters. People are, that's probably the case. Well, then maybe you can inject it, and then like the interesting thing is going to be how does that like prior knowledge, like we're going to be able to like strengthen or weaken that prior knowledge, and the question is going to be how does that prior knowledge kind of play out with how much data we have. And the intuition should be here something like, if I have a lot of data, it should just wash out my prior knowledge. Because like at the end of the day, if I have billions of examples, who cares about what I believed? I can just look at the data, that's good enough evidence. And the kind of the converse is, if I had very little data and I had like a pretty strong prior belief, then maybe really my prior belief should kind of dominate. Like if I had like just 2 data points and I was pretty confident that, the average height, because someone told me this fact, is like 160 centimeters or something, then maybe that should kind of dominate my belief. And we will see that when we solve this kind of expression. Okay, so what's next to do is just repeat the kind of example of people's height, but with this extra assumption of what the parameter, the mean parameter could be, and somehow, injecting this idea that it should be like some number, maybe between 100 to 200 centimeters. And so we repeat that, and then we apply it to the machine learning case, and then we're done for all this stuff. Then we move on to classification after. Okay. And that will not be done until after reading week. So we do a little bit of math basics. We'll start on this today. We'll finish it next class. Same with the machine learning stuff. And so let's repeat the example. The example was this people's height. And we had this Zi random variable. We said, oh, well, I think people's height is normally distributed with some mean parameter mu star and variance 1. And this was, height of ith person. And what that meant is just that, well, this distribution for a particular value of z for a particular height was the normal, this PDF was the normal PDF. Let me just rewrite it. It was 1 over 2 pi exponential of negative z minus mu star over 2. That's just the PDF of this normal distribution, which you can look up, I guess, in your formula sheet, for instance. And now we're going to assume something. We're going to make another assumption, which is what should, what's our bias, what's our prior knowledge of what mu star might be? It's going to be that prior. In other words, we're going to want to pick something for this, let's say, PDF of mu. And mu is to be treated as a random variable now, and we're going to say that mu is going to be, as you can see, our favorite choice is a normal distribution. And maybe that's reasonable, right? The normal is telling you something like, we're confident in some region, which will be kind of like the area we think it's most likely, and then it kind of dies off as you go further out. If you instead for some reason believe that there was like 2 peaks, I don't know, maybe people like it's either 150 or very likely 300 centimeters, which would not be the case for people's height, then maybe you pick a distribution like this, which would have to be like a sum of normals or something. That would be more complicated. But anyways, we make this simplifying choice of a normal distribution, and we say that, yeah, we think the average height of people is probably normally distributed with, let's say, and now you have to pick a number here. What is the mean, you think? And I'm just going to say 160. Maybe that's the average height of people if you take them around the world. I don't know. And you have to pick some variance. And here, we're actually going to make this a parameter. Okay. And why is this a reasonable place to make the parameter? Well, you could also make this the parameter, but we're going to make the variance the parameter here because we're going to say this is kind of like so what we think the average height might be. And then the variance is going to tell us how confident we are. So if the variance is very small, it means you barely vary. You're going to have a normal that looks like this, or its density. And if the variance is wide, it's going to be like this. And in the extreme case where the density is essentially like as large as possible, the variance is as large as possible, you get something like a uniform. So this is going to be kind of the parameter we can tune, and we can pick a number here too, to tune our kind of prior belief in this mean. And we're just going to keep it as a parameter because when we get to the final solution, we're going to see that it depends on this sigma squared. And it's going to depend in the obvious way, which is if sigma squared is really, really, really large, our prior is basically going to do nothing in our final solution. And the final solution, I mean this thing. And if this is really tiny, it has 0 variance in the extreme, it's going to be that the prior knowledge is going to dominate. And yeah, and so all that says is that this P of mu has also a normal distribution. Now, mu is the variable inside this PDF, so z is replaced with mu, and mu star is the mean, which is 160. And the variance goes downstairs and is 2 sigma squared. Okay. So that's going to be our prior knowledge, or prior on the parameter. And what we're now going to want to solve for is mu map, which is the map estimate of the parameter mu. And that's just going to equal to this expression, which we have seen above, with w replaced with mu. So w is now replaced with mu. Mu can be any real, well, yeah, okay. It can be any real number, but yeah, that's fine. Of course, the mean can be any real number. And this is now not for w, but for mu. Just a single number. Okay. And I guess for next class, we're just going to plug in this. We have them. Well, I mean, this is, so remember, maybe I should put this IID. So this thing is going to be this product, right, of all of these PDFs, n of these PDFs. And that's what we've seen before. And this P of mu is going to be the new thing. We're going to apply the log again, the negative log. And then we're going to work it out. You can already see that since there's a log, when you take the log, there's a product of things. This breaks up into a sum. And it turns out to be basically the same solution as before, but with an extra log of this. And that log of this, when you solve that argmax, is going to give you the regularization kind of term that we've sort of seen before, at least in the machine learning setting. And yeah, that's going to be our interpretation of regularization in a different view. It's going to really be like the regularization is going to be some thought in like what is the prior on the weights. Okay, so we'll discuss all that next lecture. I guess, what is it today? Today's Tuesday. So I'll see you on Thursday in 2 days. All right.